So the whole interesting thing about this about the idea of photons. Now we've spoken about them, the whole wave particle duality situation, because fundamentally speaking, you can think of these photons that we talk about as these waves, and that's a whole that opens up a whole new idea or a whole new wave of thinking about light, right? Because initially the double slit experiment the double slit experiment was done on light, on photons, and then the idea was then traversed onto electrons as well. And then similar results were seen with electrons, and then saying, okay, electrons are not actually particles either, but even we can represent them as waves, like in the electric field kind of thing. So,
And it turns
yeah,
out everything has a wavelength.
exactly, right? So the whole wave particle duality thing kind of got people thinking about, well, okay, if it applies to light, why can't it apply to other things? Why can't it apply to all other particles of nature? And interestingly enough, all other particles of nature, these force carrying particles, have these fundamental wave like properties. And this wave particle duality nature gives us a very succinct way to understand it. Now, why though? Because waves, so when we represent particles, we have a position and we have a momentum. We have those two variables defined. When we have a wave, however, that's not the case. We can have a varying momentum and a varying position. Now, when I say varying, that might make not much sense to you, but a nice way of thinking about it is if you're trying to measure it and it's always moving back and forth between 3 and -3. So it's like moving back and forth between 3 and -3. So it's kind of like it's an uncertainty of position. So it's kind of varying between different positions. And the same thing is happening with its momentum. And that fundamental property of it being a wave is what allows us to transition into quantum mechanics, right? So moving into quantum mechanics is when we realize these uncertainties and quantize these equations, right? And the whole goal in quantum mechanics is to quantize an equation of motion and to understand, okay, this is happening in the real world. Let's see if it happens in the quantum realm as well. So then they applied it to the quantum realm, understanding light and understanding all of this whole deal. And turns out, again, this whole wave particle duality situation with all these particles fundamentally being waves can directly be applied into quantum mechanics, right? Now we don't want to maybe get too deep into it, but the most important notion of quantum mechanics, a very important notion of quantum mechanics, is the wave function. And as described by its name, it's a wave. It's a function that's an oscillating function. So it's a wave. And making the connection between this wave function, what we've defined, and what we see in the real world, this wave particle duality, is what allows us to quantize light, right? And make that connection between them.
Wait, in what way does the wave function allow us to quantize light?
No, I'm saying the fact that light has a wave-like property, and obviously we've defined quantum mechanics around these wave-like properties. So we have a thing like the wave function. So I'm saying we can apply the wave-like properties of light into quantum mechanics via things like the wave function is what I'm trying to say. Right? Like via using those states, we can apply it in quantum mechanics.
I feel like those are two different things though. Like the wave-like properties of light and like the wave function of an electron. It's not really the same, because an electron
I'm just
can
trying to
have
make the
wave
relationship in quantum mechanics. Because the wave function is fundamentally a quantum notion, right? So I'm trying to make the connection between the wave function in quantum mechanics and the wave-like properties of all these particles. So that's what I'm saying. We can connect it to quantum mechanics via that waveness.